Uh, my brain just doesn't do its job anymore. It has one job and it's for me. Uh,
Good morning.
Good morning.
Hello, hello.
This is working like a treat today.
Hey, hey.
That sounds rough, Eduardo.
Monday. It sounds like Monday.
It sounds
Not
like
ready to
Monday. It sounds like
Monday.
Monday. You come back to Nijmegen and you tell me. Like,
Oh, the forever gray.
the forever gray and also rainy shit we get until February, March, whatever, until we kill ourselves.
The
Yeah,
Italians even have a word for that, right? Meteoropatico. You're feeling the weather, not in a
Uh,
good way.
it's not it. It's more than that. I also destroyed my mocha this morning, so
Ooh,
mm.
now that explains the grumpiness.
yeah.
Now you're dependent on MPI coffee, and we know you love it.
Yeah, she's basically a death sentence. So
Wow, that's harsh. There's worse.
yeah, maybe North Korea, but
Mig is joining us from space again. Love it.
are we already recording, by the way?
Yes,
Oh
you're swearing
shit.
in public.
Okay. I guess our listener will understand.
It's time to behave yourselves.
Where's Anna when we need her?
That's just gonna make it worse. Anna,
Yeah,
you
but
kind
she's
of
worse than me, so by comparison, I look good.
never on record. Only in the chat. Anyways, let's get started. Nice to see that Zoom is working again. And good to have you all back in the same room without any shenanigans of going back and forth. Now, today I'm sharing a paper and you need the link. Hang on. Dum, dum, dum. Where did you go? Here. Tuck. There's the link for you. And I thought this was quite an interesting paper because, well, it's not just one reason, there's a couple of reasons why I think it's good. But it basically tackles a fundamental question, which is, does image resolution hold the key to better tractography? And the underlying assumption is that higher resolution is always better. And this is part of a special issue published in Brain Structure and Function, where you have a series of tractography papers that discussed several questions that arose during a meeting in Corsica 2 years ago now with the International IST, International Society for Tractography. Here we go. And what we did at the time is we stood up and everyone presented one slide as a did you know slide and shared one exciting piece of research. Now, in this one, Tim Derby, Laurent Petit, and Christian Boulot discussed this question that we should be rethinking tractography and neuroanatomy in tandem. And it's quite interesting. They suggest that our acquisition should be tailored to our anatomy, meaning that the authors challenge the idea that higher spatial resolution is always better or means better tractography. And what really matters, according to them, is that you match your voxel size to the anatomical scale of the structure that you're studying. And that's a concept they call structural image resolution limit. And that's quite a cool idea that could have far-reaching consequences. Now, I'm quite happy that it's something we've intuitively been doing in our labs. Hang on, was it Q1? No, command one? Command one. Here we go. Single page, that's better. So save your order scrolling and go straight to the figure that you have here. And there's one figure in this paper where they try to explain a couple of the things they see. So the first one, if you look at panel A, the overall idea is that there is no one size fits all. So your tractography should be tailored to the structures you want to look at. And that, very broadly speaking, means if you want to look at the big highways in the brain, you need a different acquisition than if you want to look at smaller subcortical structures, or if you want to look at U-shaped fibers, for example. And that's something we've always done in the lab, where we tailored the algorithm to the anatomical structures. One of the things to consider, for example, is the curvature, right? If you have long tracts, you don't bend as much and you don't turn. If you have U-shaped fibers, then within a few voxels, you have to make that turn from one gyrus to the other. But what we know is that tractography is biased by a couple of things. One of the things I just mentioned is the angular resolution, but also the signal to noise ratio that we have in the data, and generally our modeling approaches, meaning which type of algorithm we use. And for all of you who've been to the workshop 2 weeks ago, you now have a good overview of all the algorithms and their pros and cons. But here, what they say is that we also need to look at actual spatial resolution, so the voxel size in millimeters on top of that. And the idea here is that in theory, smaller voxels should capture finer details, but in practice, smaller voxels also mean that our SNR is lower, and that also means longer scanning time. Which you all know I've been in the scanner for 10 hours for exactly that reason. Because it takes a long time to acquire smaller voxels. But the point they're making here is that there is a sweet spot depending on the anatomical target of interest. And they show it in panel A here, where you see that at a lower resolution, so chunkier voxels, you see more blurring. And as we increase the resolution, you see more details. But if you're interested in the highways, then this is actually not necessarily a good thing, because the more voxels you have, the more decisions a algorithm has to make at every single voxel, and that can introduce a bias, and that can also, I think they use the word decay, if I'm not mistaken, decay the tract over time, meaning that the longer the tract, more unreliable the reconstruction may become if you have too many steps in between. So the core concept then is that the structural resolution should always match the anatomical resolution. So if you're interested in the big highways in the brain, then a lower resolution, meaning bigger voxels, is probably preferable. Whereas if you're interested in smaller structures, then a tailored and structure-specific acquisition may be worth it. And that is what you see in panel B. So the first visualization are U-shaped fibers of the cortex acquired at a resolution of 1.5 millimeters. Then you see the trigeminal nerve, which is quite a small nerve, and is surrounded by cerebrospinal fluid, which is not easy for tractography to deal with. But if you zoom in and really dedicate your acquisition to that structure of the brain, then the resolution is better than if you apply the one size fits all for the whole brain acquisition. And then we have this beautiful hippocampus image where, sorry, I put some of the text over so you have the most important information from the paper there. But you can see that's beautifully reconstructing the hippocampal structure here. And the idea is that this is not a whole brain acquisition where you try to get the big bundles and then zoom in on the structure, but this is a dedicated acquisition just for the hippocampus. So you set your field of view to the anatomical structure of interest, and you can see that the scan took 6 minutes at a low B value of 500. And they don't have, oh yeah, here, 20 slices to align to the hippocampus. So it's very dedicated to the structure of interest. Not all the structures have been mapped in that way. There's more and more positions coming out, especially for diffusion in the gray matter as well, which the hippocampus is part of. But you can see the advantage, and you can also, if you compare the two, you see that the information is qualitatively different between the big picture acquisition of a whole brain for the big tracts and the smaller tracts. The other point they're making is that it's also interesting to just look at a FA map, and that's what we see here. So this is the same brain. I think it was a macaque brain. Can't see it here. I think it was a macaque brain, but they acquired it 3 times at different resolutions. So you have 150 microns, 80 and 60. And what you can see is that the
It's a model.
layering of the fibers becomes more and more obvious. And you can see, for example, here, the beautiful interlayered structure between the green blobs here that is completely lost at a lower resolution. I always get my low and highs wrong here. But again, tailored to the anatomical structure of interest that you want to look at. Now, why did I choose this paper? Well, A, because it's part of this special issue, which has a lot of interesting papers, but I also think it provides an elegant conceptual framework in terms of the structure resolution limit, that rather than just applying a blanket, this is the best acquisition for everything, you actually consider what the anatomical structure of interest is that you want to image, and then you tailor the tractography accordingly to have the best possible outcome for a given structure. What I also quite like is that it's a very applied paper in a sense that it offers concrete and feasible examples, and it always brings it back to clinical scanning time. So there's always a reference how long the scan will take in a clinical setting, and it nicely bridges the technical details on the acquisition side with new anatomical interpretation, which is something that's often missing in diffusion papers. So I'm quite happy to see that. That said, what is limiting is that it's a prospective paper, so there's no new data. It's not an empirical study. Most of the data they show, as you can see in the figure legend, is reprinted from previous works. And it also doesn't fully address the new kinds of resolutions that we have, like the super resolution or the model-based approaches that may recover some of the subvoxel structures as well. But again, it's a perspective piece. There's only so much space you have for the ideas. And then I also thought it's quite interesting for those of you doing language, because at the language networks, you can also look at large scale language pathways, in which case for example, 2 mm resolution is sufficient to get tracts like the arcuate or the inferior front occipital fasciculus. But if you're more interested in superficial white matter, U-shaped fibers, hippocampal subfields, then you would need a higher resolution that is tailored to the specific regions. And that is all I had for now. Happy to discuss. Any questions? Yes, Chris.
So I don't think they talk about it, but do you have an idea about super resolution? If there would be a way, so in because tractography is a reconstruction from the imaging, but if we take the imaging, the raw imaging, we can super resolve it to try to increase, to improve the resolution. Do you think that would be possible So if we have a resolution that is not adapted to one, as you said, like a specific question, would there be a degree where we can maybe increase it slightly to get what we want, or do you think it would just be made up by the technique, because it's usually machine learning, so of course it can be recreating things that don't exist in the actual image. Do they
Yeah.
discuss that?
Not in as much detail, no, but they do make the point that unless you tailor the acquisition, it's very hard to pull out the signal retrospectively. And they also make the point that a lot of the algorithms interpolate the data, and that basically averages the signal per voxel, and then there's no way of retrieving the raw information anymore.
Mm.
So yeah, here. It's in the first Did You Know section and the introduction, where they basically talk about the information having to be there in the first place rather than you being able to pull it out post hoc.
But that's interesting because I mean, this is very debated for the super resolution. People are saying, oh, maybe it works, maybe it doesn't. But that's interesting to say, like, straight away, the signal is not there anymore. So, like, you would be inventing signal if you were trying that.
But the question still is, would it work, right?
Yeah, but they seem to be saying, like, the information is gone. So,
But could you reconstruct it with machine learning, I guess is my question.
I mean, yeah, that's the hope with the super resolution, but a lot of people are skeptical.
It's our job to be skeptical, yet we
Yeah.
try. Eduardo has a question as well.
Yeah, I mean, I don't know if it's a question. It's kind of related to what Chris was saying. Because as you go up with the resolution, you increase also the noise. So did they say anything about improving the quality of the sequence along with the resolution, so that if you go up in resolution, you still get enough signal to reconstruct stuff? Because that's a problem with super high resolution, right? If you only go up with that, then the noise is going to take over at a certain point.
So I think they made that point somewhere, that we always push for like higher gradients, faster acquisition time. But resolution is a byproduct most of the time rather than a forethought. And they have across the paper, they usually say how long it would take to acquire it, which is the nice application bit where they bring it back to clinical usability as well, showing that depending on what you need, you don't actually have to push your resolution to the point where you end up in the scanner for 10 hours, which is not clinically feasible. But if you're only interested in the big pathways, then a lower resolution scan is perfectly fine, which most of the time in the clinic is what you need anyways.
That makes sense. Also, you took over Marcelo Neuroccino.
I just saw that in the chat. Sorry, Marcella. I looked at the schedule.
No, you didn't.
Oh, I did.
No.
Was it my turn next week?
Yes, it
Yeah,
was.
no worries. We will talk
You
it.
should have said something, Marcella. Well, then you can do it
We
next
were
week.
live. We were live.
Pirate in
Eduardo can
Neuroccino.
swear when we're live. You can tell me off when we're
I
live.
Fair,
You were
fair.
no, no, it's fine. You were so excited. I'm gonna share my screen. So I said, okay, not me today.
Sorry.
No, but it's very interesting paper. So
Are you available next week then to take my slot?
no, but no worry. We can continue with the paper. I will solve it. No worries.
Sorry.
All good.
I looked at the schedule and I thought it was my turn, but I do apologize for stealing your slot.
No worries at all.
But if you're not available next week, we may call on Anna as our joker because there was a slot where two people prepared a paper as well.
Okay, who was the other person?
So Anna prepared a paper, but who was the person who presented? I don't
Observing.
know. But we can fix that later.
Yeah, of course.
Sorry. Do you have any more questions on the paper?
I have another question.
Mm-hmm.
I'm wondering if beyond the spatial resolution, there may be other parameters that would be important depending on the kind of acquisition that a researcher would be interested in. Things like the b-value, number of diffusion directions,
So these
gradients.
are parameters that are always of interest, right? And we generally say the higher the better for the b-value. But again, here it depends on the sample that you're imaging and the tracts of interest. So if you just want to look at the arcuate fascicles, for example, then you can get away with less than 60 directions and a b-value less than 1500. If you want to look at the three SLFs, for example, then you have to push above 60 and above 1500 because you need to resolve a lot more crossing fibers. So these parameters are relevant, again, depending on the research question and the sample that you're looking at. If we bring it back to the clinic, then you simply may not have the time to go for a super duper high resolution, fancy multi-shell acquisition, right? Because that usually takes time. The hardware is improving, the software is improving, we're getting faster and faster. So now you can acquire in 10 minutes what used to take an hour, right? So that is a good thing. But again, all those parameters depend on your research question, your cohort of interest, and your timing constraints.
Sweet, nice. Thanks for the little overview. Great.
Any other questions you may have?
But do they have a take-home message in the end, like don't go too high unless you need it or something like that?
I quite like it. So they pose a question in the beginning. Does image resolution hold the key? And then when you go to the discussion, sorry for the scrolling. The short answer to whether image resolution holds the key is yes.
Yes, okay.
Quite like it. So I guess that's their take-home message. It does matter.
I have a question. I think
Mhm.
yes. So just curiosity based on the last the previous week during the conference. Do you think there is an agreement based on like about this in the community of DTI, or it's just like something that they agree like as authors of this paper, or is something that is really discussed among like across the most of the members of the community? Because I feel that there is the idea I had is there are a lot of different of course opinions, ideas based of course on research, but that seems not to be like a lot of agreement. So yeah, that's my question.
So this was supposed to be a consensus meeting, right? So we all
Okay.
met. You
Nice.
had computer scientists, you had anatomists, you had clinicians, pure tractographers, and we all came together and we had those different questions and we discussed them. And the idea is that those papers in the special issue are also written by the influence of different people.
Perfect. Okay.
So in a way, these are supposed to be consensus papers,
Mhm.
but they still reflect a small,
Yeah, I guess it's always the majority. Maybe
correct.
there's also small points, I guess, that there is no agreement, but yeah. Okay,
Yeah.
cool. Thanks.
You just see how the mishap happened looking at the schedule that it is now fixing. Leah.
Hi. So I was thinking that it would be like so helpful to have like, the acquisitions like parameters that people can use. I was looking, for example, the trigeminal nerve is something that neurosurgeons ask me so many times because sometimes they have to access there through the nose and it's really important where it is. So here in the paper, it's just a kind of a review, like or there are all the parameters somewhere.
So I'm not aware of a database for parameters, but that said, this is based on published work. So I'm
Yeah.
assuming if we go back, it should be ideally, well, you can either have a chat with Alex or you can check the paper if you find that specific acquisition.
No, but in general, I think it's really helpful. Also, like more information would be really helpful to also implement and try it in different scanners, different brands.
So Flavio, in his consensus paper in brain structure and function, has something like that, where he has compared the different scanners across different sites using traveling heads.
Oh.
And it's quite beautiful to see the difference, but also the consistency in anatomy across scanners. So the variability between people is larger than the variability that you introduce by using a different scanner.
Oh,
It's quite
that's great.
it's a beautiful image, and it's in the consensus paper as well.
Okay, cool. I'll check it out.
But you're the perfect person to come up with a diffusion sequence database.
And indeed, it would be helpful also because I need to implement like new DTI scans, and so I need to
Yeah.
review, and so that would be helpful to have it the review.
There you go, a new project for you. Cool. Any other questions? No. Okay. Well, have a look at the special issue. There's many papers like this one that are quite interesting on all the various topics. So you have comparative anatomy there, you have developmental imaging, you have the benefits of anatomy. Do we need it? It's all discussed there, and it's, as I mentioned, somewhat of a consensus special issue among the community. If there is no further questions, just a reminder that we have a CNS talk this week on Wednesday, 4 o'clock. And see you next week for the next Neuroccino to be seen who's presenting again. I'm sorry I stole your spot. Have an exciting week and see you on Wednesday. Bye.